Consider the proper steps for solving these continual compounding problems, particularly if what we need to know in a particular instance is a rate or a time. First, we'll go over the steps, and then later try to go over them in more detail so that we understand what we're doing instead of simply doing it by memory. We begin with our now familiar continual compounding formula. I borrowed a problem from the last class. Let us suppose we have an investment of $200, and over a period of 7 years, it's going to turn into $400, and we wonder what rate is required to make that happen. So we have an unknown in either the rate or the time, the rate in this instance, and we want to solve. And mostly your ability to solve algebraic problems is pretty good. You know what to do, but to have an unknown inside a power, that's a little tricky, that's unfamiliar. So that's the main thing we have to do. What do you do with an equation when your unknown is inside a power? How do you handle it? To go back to where we were, there's our formula, and then this is simply the same with the knowns put in place of their variables. And therefore, we identify our x, the rate, which is what we're looking for. How can we unpack that? Well, you know how this works, and our goal for these steps has to be to get x isolated by itself and make it equal to something that's entirely made up of known quantities. Now, that's what we mean by solving. The first thing to do, you're probably ahead of me, we see that the e raised to a power with our unknown in it is a problem, but we've also got a simpler problem. The whole thing is multiplied by 200, and that's in the way of getting an isolation for x. So we'll do what we do. We divide both sides by 200, and that will take the 200 out of the right side of the equation and move it over to the left. Now we're one step closer to having x isolated on its own. And the next step, you're probably again ahead of me, we can take that fraction 400 over 200 just reduces to the number 2. So now we have e raised to a certain power is equal to 2. And now we get to the place where we need something new, some new tool, not the kind that we use all the time. And what do? Well, we simply take the natural log of both sides. And what we've been doing in each stage is to do something to both sides of the equation. So we go from one true thing to a slightly altered true thing. And we always want the reverse of whatever is in our way. So we had our unknown multiplied by 200. We did the reverse of that, the inverse of the opposite. We divided by 200. Now we've got the unknown as a power of e. Well, how can we reverse that? How can we do the opposite action of raising something to a power of e? Well, that's exactly what the natural log is. So in order to make the next step, we will do what's crucial, and probably the only thing that's new in all of this. We'll take the natural log of both sides. And what do we end up with? Well, you punch this into your calendar, or your calculator rather. You take the natural log of 2 and you get a number like that. It will give you lots of decimal places. We won't put e to the power of x times 7 into the natural log because we understand natural logs well enough to understand that if you have e raised to a power and you take the natural log of that, you just get back to the power. That's by definition. And that's why we're interested in natural logs in this case. So if we take the natural log of the left side, it will be equal to the natural log of the right side. This is what the left side comes down to. That's what the right side comes down to. So, with only one unfamiliar step, we are at this equation, and you all know as well as I do what one does in a case like this. And when we've worked out, divide each side by 7, and now we've reached our goal. X is isolated. We have it set equal to something that is known. And if you don't like that fraction, you can get a decimal version of it out of your calculator. And it's approximately 10%. And that's what we wanted all along. This problem again with t is the unknown to get a little practice. So again, everything about the problem is the same. I put in an approximation for our result for the rate. It was almost 10%. And now what we don't know is the time in years. So first step is the same. You put in what you know wherever you can, and you identify the unknown. And now our time, we still have the basic problem that our unknown is a power that e is raised to, and we have to get beyond that complication. But the first steps work just the same way. We isolate the e raised to a power to get that much closer to x all by itself. We simplify the fraction, and then we take the natural log of both sides. The natural log of 2 remains what it was, and taking the natural log of e to any power simply yields that power. The final step of the algebra is different, not in any way that's going to cause you any problems. We have 0.69, etc. is equal to 0.0099x. We want to get x by itself, so we divide both sides by 0.099, and we get a little bit less than 7 years. If we wanted to be more careful about the longer approximations, some more decimal places, we get as close as we need to the approximate answer, 7 years and 10%. Do another problem just for practice. You could suppose you're on the steering committee for the university, trying to help the university plan for the future. And they're counting 1,200 undergraduates registered at whatever time that is, and they're wondering, can they bring that up to 2,000? Let's suppose they increase enrollment by 5% every year. How long would that take? That is to say, t, the number of years, would be our unknown. So if we fill out the continual compounding formula with what's known and isolate what's unknown, we get that. We go through the familiar steps, get the e figure by itself by dividing by p sub 0. That can be reduced to a fraction. It's 1 2/3. That would be that's the problem that is being posed. If we start with 1,200, how can we increase enrollment by 2/3? And then we get to the new step that we're trying to get used to, since we've got that equation, but our unknown is inside a power of e. What do? We take the natural log of both sides. Your calculator will give you a number like this, depending on how many decimal places you want to bother with for the natural log of 1 2/3, 1.66 repeating. And of course, we know this by definition. We take the natural log of e raised to some power, we simply get the power. That then is the simplest kind of algebra we can do. You all know how to solve for x in that situation. What you get is 10.2 years. So you could tell the steering committee at 5% it would take over 10 years, that if they could keep that level of growth up, they would expect to reach their goal in the 11th year. Now, it should be fairly simple to take one step forward in understanding and to recognize why we do things this way, why these steps are what they are. This to do that extra to understand what you're doing is crucial, both because you're a thinking human being and you shouldn't do things without knowing why you do them, but also because you won't be able to remember the steps permanently unless you connect them in some reasonable order until you see why they are where they are and what they're doing. And really, what we can see from solving these problems is that you're doing algebra in the normal way with one new tool, the natural log in relation to E. But you're very used to solving these equations, and you maybe do it correctly without thinking about what you're doing. But when we solve for x, we always have the goal, of course, of isolating x and making it equal to things that we know the value of. And so, as with any other algebra, with each step, we want to get closer to this, where we have our x isolated by itself equal to some particular number. And in order to do that, every time we face a complication with x, then you do the inverse function, you do the opposite, you undo what's been done so that you can get nearer and nearer to your goal. So that is in fact what we did here. The whole E term with our unknown in the power was multiplied by something. And that was a complication that we wanted to get rid of. So how do you undo a multiplication? Well, by the opposite function, which of course is dividing. So we divided this whole side of the equation by the number that was in our way, 1,200. It ended up over here, but that's okay because we've just got a collection of known things. Even if it's a little complicated, we can solve that problem. And so all that we've done as an innovation is used a new inverse function. And we know that when you're dealing with E and raising E to this power or that power, then the natural log is by definition created to be the inverse of that. We just remember what this means. We got some number, and we take the natural log of it. What we get out is the power that E needs to be raised to get that number. So if we take the natural log of E raised to some power, we simply get the power. That's going to be true by definition. So when we have known things on the right side and E to a power on the left side, we do what we always do. We ask, what's the complication? Well, we have E raised to a power, and our unknown is buried in that power. How do we get rid of it? By doing the opposite of what's being done to it. Well, it's in a power that is changing the value of E, or it's in E raised to a certain power. The opposite of that is the natural log. We know we can go from one fact to another, from true equation to a slightly altered true equation by doing the same thing to both sides. And so we take the natural log of our E term, we take the natural log of the number on the other side of the equation, and that yields us a new equation, and a little bit of trivial algebra will solve it. Keep that in mind, and you will know what you're doing, and you can recover this formula when you're on the board of this university or in some other privileged position and you're asked to answer some of these questions.